Welcome to this biogeochemical training. I'm Gianpiero from the National Institute of Oceanography and Applied Geophysics from Trieste in Italy. And it's a pleasure to me to introduce to this exercise about the biogeochemical Mediterranean Copernicus project. During the exercise, we will use Copernicus data to visualize maps, section and time evolution of some of the variables of the biogeochemical product, and we will focus on the Northern Adriatic Sea. Two notes about this notebook. Jupyter environment is a web server environment, so you don't need to install anything. You have just to follow the exercise using the run button at the top of the of this page. This Jupyter notebook is a document that contains text and codes. The code is a Python, and for executing the code you have to run the code by this button or using the Shift Enter keys. During this exercise I will introduce the data, the biogeochemical data, and we will use this data to plot maps, transit and time evolution in 3 different exercises. The main objective of this exercise is to explore how to use the biogeochemical data for looking at some of the typical dynamics of biogeochemical dynamics in the Northern Adriatic Sea. In particular, we will see a winter map showing the surface gradient due to the current dynamics and the coastal open sea frontal system. Then we will explore the depth of the Adriatic Sea by showing some transit, one for winter, one for summer, for nutrients and for chlorophyll. And then also we will plot a temporal evolution of partial pressure of CO2 and the CO2 RC fluxes. Very interesting, this exercise use the same location and the temporal frame of the physical exercise, so you can combine the results of the 2 exercises in order to see the impact of the physics on the biogeochemistry. In particular, the impact of the water confinement on the spatial gradient of nutrients, or the effect of winter with vertical mixing and summer stratification on the vertical distribution of the biogeochemical variables in the water column, and the effect of the seasonal evolution of temperature on the solubility of CO2 and on the RC fluxes at the RC interface. The data that we are going to use during this exercise is the biogeochemical product for the Mediterranean Sea for the analysis and forecast for the near present and the 10 days in the future. And this is the domain of the model that covers the entire Mediterranean Sea. The model is the MED-BFM model system, which is a coupled model of the physical OGSTM model and biogeochemical BFM model. And also the system has a data simulation scheme, a variational data simulation scheme for the chlorophyll from satellite sensor. And this system, the biogeochemical system, is coupled to the physical system, which consists of the coupled NEMO Waywatch 3 and Ocean Bar data simulation scheme that is run by the CMCC. This frame that you can find on the web page of the biogeochemical product in the catalog contain all the information about the product, particularly the list of the variables that are the chlorophyll concentration, the Phytoplankton concentration in terms of carbon, the dissolved oxygen and nitrate, phosphate, the net primary production, the pH, the dissolved inorganic carbon, and for the CO2 system, the partial pressure of CO2 at surface and the surface flux of CO2. And here are other information about the product. All the information can be retrieved in the official web page, in the Copernicus web portal, and there are two very important documents that are the product user manual and the quality information document that should be read before using the data, and contain all the information needed to use the data and to apprise the quality of the data. For this exercise, we use a subset of the Mediterranean data. We focus on a particular area limited by this latitude and longitude limits. We will use the monthly data and only 3 data sets regarding the phytoplankton, the nutrients, and the CO2. And only 2 time frame, the January of 2019 and September of 2019. So we start the first exercise, which allow us to plot a map of surface of nutrients. Before doing that, just a few words. The code that are in this green cell are Python code. Python is a language very common in oceanographic and atmospheric science, and you don't need to install anything. Everything is installed, but you need to know that this code needs some modules, some libraries that are listed here. We can go through all this information that you can read by yourself, and to run the code, you have to press the run button here, and you see here a number appear, which means that the code has been executed. In this case, this instruction is used to ask the system which is the version of the Python installed. In this case, the version is the 3.7.3. In the case you have to install something, you have to follow this instruction, but we don't need that. And we can start to execute the code that will allow us to plot a map of nutrients. So first we have to import the modules, and we execute all these code cells. And the next cells are to get information about the data that are already present in this web server. So you don't need to download the data. They are just saved in a particular directory in this web server. For example, the next code cell means to list the files that we are going to use. The first one is a netcdf file containing the CO2 dataset for the particular period that we selected, and the next 4 files are 3-dimensional dataset for nutrients, phytoplankton again, and again nutrients for the 2 time frame. One in January. Here you have the date of the datasets. This one is 2019 January, and this one is 2019 September. And then the next cells allow us to to open the data. In this case, we are going to select only the nutrients and the phytoplankton data sets. Here is instruction for opening and reading the data. We here select the winter time frame, and in the next cell we can get information about the content of the file. So it tells us which this info that follow the name of the data sets here tell us the dimension, the variables, in this case the nitrate and phosphate, and a list of attributes or metadata that are inside the netcdf file and are very useful to have additional information about the dataset. We can ask just to list the variables or to list the coordinates inside the dataset, or to list a specific dimension, in this case the depth. And here we have the output of this instruction. We can get the dataset for phytoplankton carbon biomass and chlorophyll. Again, here we have all the list of information regarding the coordinates, the variables, and the attributes. And again, we can just list the variables or the coordinates. You can try by yourself to see which are the method and the properties available for this particular dataset. So you have to copy this piece of code. You put here inside the executable cell, and using the tab key should appear the list of all the available attributes and methods. For example, if we want again to look at the dimension, you just select the dims and then we press run, and here is information about the dimension, which we have only one time frame. We have 125 depths and 380 latitude points and 1005 longitude points. The next Python cells allow us to make some configuration, some setting that are needed to run the code for plotting the map. We just execute it. You can read the comment inside the Python code that are this kind of lines with the hashtag at the beginning, and to understand better what the code does. So we configure some elements of the plot here, executing this cell, and we are almost ready to generate a map. This is a very long piece of code that will produce the map. We execute it, and a map will appear. And this is a winter map of nitrate that shows the effect of the Western Adriatic current that keep the nutrients that are discharged by the rivers, the Po River here, but also the other rivers along the northern coast, and keep all these nutrients in a very narrow strip along the Italian coast. And here we have the highest concentration of nitrate, while the rest of the basin in the central and eastern part, the concentration is quite low. This is a typical condition in winter, with a frontal system from the near coast to the open open area of the basin. Of course, you can go back to this Python shell and changing the variables that you want to plot, or by the coordinates and other particular features of the Python code and of the variable, of the plot. In the second exercise, we want to plot a transit. So we need to fix a point, which will be somewhere here in this particular location, and to look at the vertical dimension of the project, of the biogeochemical project. So we execute these command cells in order to set what is needed for the Python to produce a transit plot. We generate a function that is called a plot transit, since we are going to use more than one time, so it's better to create a function. We execute it, and now we are ready to plot the first transit. The first transit will be the nitrate transit, and we selected putting this 0 the first time frame, that is the winter, January time frame. We execute this function plot transit using this data and using these numbers that are for the color bar limits. So we execute it, and we are able to generate this very nice transit of nitrate in January, where we can see the shape of a column that is completely mixed by the vertical winter mixing, and with the higher concentration in the western part along the Italian coast because of the input from rivers and the confinement due to the western Adriatic current, while the rest of the basin has a very low value of concentration of nitrate. We can plot by just changing the variables. Here we now want to plot a phosphate, and we put 1, which means the second time frame, which is the summer condition. We use again the function that we defined before, and with different limits for the column bar. We execute this cell, and here we have a typical condition in winter where all the surface layer is depleted while the high level of concentration are only in the bottom, and this is because of the use of nutrients in the surface layer by the phytoplankton, and while the accumulation occur in the bottom because organic matter after sinking is remineralized. And this stratification is also consequence of the vertical stratification of the water column. So you can compare with the physical exercise at the level of the mixer layer depth. That is almost the same as this nitric line depth. Now we change the dataset. We look at the chlorophyll to see how the phytoplankton react to the availability of nutrients. So first we plot the winter section of chlorophyll by selecting the dataset of chlorophyll and the time frame 0, that means the winter one, and we use the plot transient function to plot the data. And again, we have a distribution of phytoplankton that is very similar to the one of nutrients. And if we want to plot a summer, I invite you to do it by yourself, and for doing that you have to copy this instruction and put within the cell, the executable cell. Again, it's already here, but you can do by yourself. And we selected chlorophyll as the variables, the time frame number 1, which means the second time frame, that is the summer one, and using the plot transient function we generate a section for the chlorophyll in summer, which appear very different from the winter one. And here you can appreciate the presence of a subsurface layer of higher concentration of chlorophyll, which is called deep chlorophyll maximum. And this layer is appear where the nutrients are present. If you come back to the transit of phosphate, here you have the presence of nutrients, and is the same layer where we have the higher concentration of chlorophyll in summer. And so, because phytoplankton needs nutrients to grow. And the third exercise is about the plot of CO2 concentration at surface and the time evolution of CO2 fluxes at the air-sea interface. For plotting this time evolution, we need we use another data set. We use the data set regarding the CO2. Here you have CO2, which means data set for the carbonate system. We are going to use daily data. We use only one point, so we selected a specific area, and we are going to use daily data for the entire 2018. So we will see a seasonal cycle of CO2 partial pressure and CO2 fluxes. There are two aspects that must be considered. The first one is that the Copernicus dataset use some convention for the variables, and so for example the flux of CO2 is positive for a downward flux, so it means sink of atmospheric CO2 in the ocean has a positive value, negative for outgassing from the ocean to the atmosphere. And also the units of CO2 is Pascal. And so if you want to convert and use different units, you have to make some calculation by yourself. For example, if you want to use microatmosphere or part per million, you have to multiply for conversion factors. The next cells are just to set all the information for the Python code in order to read the CO2 dataset and to set all the setting for the time evolution plot that is in this Python code here, and this is the results of this Python code for plotting a time evolution for a particular variable in a particular point. In this case, we have in red the partial pressure of CO2, and you can appreciate the marked seasonal cycle, which is due to the solubility of the gas driven by the seasonal cycle of temperature. So solubility is low in summer and we have higher partial pressure value, and solubility is high in winter when the value of partial pressure is low. And in blue we have the flux of CO2 at the RC interface. I just remind you that positive value, this is the zero. Positive value means a flux from the atmosphere to the ocean. So in winter, the marine system acts as a sink of atmospheric CO2, while in summer we have negative value, means an outgassing from the marine system to the atmosphere. Very interesting, I think, is these two peaks. These are due to very windy days that contributed a lot to the flux at the RC interface and can contribute significantly to the annual budget of the CO2 exchange between the atmosphere and the marine system. Yeah, this was the last thing I wanted to say. I thank you for being here, and I hope you enjoy it.